Hi, this is Qian from Physics 2, Section P3, and this will be my Test 2 wrap. So one question I had some trouble with was problem 4 from Test 2. And in this question, we have a straight wire with a current running in it. We have a compass above the wire, and because of the current, the compass, which was originally pointing north, is deflected to the left by an angle of 8 degrees. In addition to the picture we have that I copied over, I also drew a side view of this situation. So part A of the question asks, in which direction is the current running? And I had an issue with this problem because I had treated the compass to be below the wire, but in actuality the question is asking for the compass above the wire. So what that does is it gives you opposite current direction if you put the compass in the wrong place. So right hand rule, we're going to have, let's assume the current is running north, running upwards, and our observation location is above the wire. That means my current's this way. I would bend my hand towards the observation location. That means I would deflect to the right. But that's not what happens here. So that must mean my current is running actually in the opposite direction, this way, bend towards the observation location, so that means it's pointing to the left. So for part A, using the right hand rule and putting the compass in the right place, we can say that the current is running from north to south, from up to down. So for part B of the question, which was determine the magnitude of the current flowing through the wire. So in order to do that, we have, I'd like to draw a diagram. So we have a magnetic field from the earth that's pointing upwards. B of earth equals 2e negative 5 teslas. And we have a certain amount of magnetic field coming from this current from the wire that's causing our needle to deflect 8 degrees this way. And we're solving for this one right here. So what we can do is use trigonometry. We have this angle, we're looking for the opposite triangle length when we have the adjacent triangle length. So if we did tan of 8 degrees equals opposite over adjacent, we can isolate B wire, what we're solving for, to be tan of 8 degrees times 2e negative 5. And if you plug this into your calculator, you would get B of the wire is 2.81 e negative 6 teslas. But how does this help us in finding the current in the wire? Well, from the formula sheet, we know that the induced magnetic field is equal to our magnetic constant times 2 times the current over R, which is how far away our observation location is from the current. So we have our wire, we know this constant, and we know how far away we are, and we're solving for I. So it looks like we have all the information we need. So if we plug all of this in, 2.81 e negative 6 equals 1 e negative 7, which is this constant, times 2 times I divide by our R value is how far away the compass is from the wire. And from the question description, we see that it is 4 millimeters. So if you convert that into meters, it would be 0.004. So now we're solving for I. We move all of this to the other side. We can get that I equals 0.0562 amperes. And again, it's running from top of the wire to the bottom of the wire. Thank you.